Started recording. I believe we are 33. I think it's a decent people are here. So, okay. Does anybody have any error while populating the OD sample, OD energy samples? I'm sorry, this is wrong. OD energy sample. I assume that nobody has an error, which is so good. So you go to the PhysiCell folder, make clean, make data cleanup to clean the data. Make clean is just cleaning the link files and executables, and make reset, just resetting it. So this is a very powerful command. So I am so kind of like be careful while I'm using make reset. And make this project is showing how many project we have and the name of them, and make all the energy sample will populate the LibRoadrunner sample project, the supported only supported LibRoadrunner project, and then make will compile, and then before, if you didn't install it, it will install the LibRoadrunner for you. Okay, so let's go and have a model in here. So again, maybe we can just go back in here. We will have 3 substrates, 1 energy, and there will be some custom data will be used in updating updating phenotypes. So as a demo, we will use negative 500 500 x. This is right, and then the dx, dy, and dz is 20. Those are valid, and the maximum time will be 2 days. Oh, sorry. I think my brain is not can calculate right now. It's 1,440 minutes, and the thread is your choice. I have 12 threads, so I think I will use my 8 thread for it. I would like to save my data for both SVGs and full as like 30. In each 30 minutes, both type of data will be saved. So when we go to the microenvironment, I just want to create the first one, the substrate. Let's rename this one as an oxygen. So the capitalization is matter. So therefore I am just using small cases, and glucose and lactate. So I just created the substrate, and let's go back to the oxygen. So in this oxygen, in this in this demo, this domain is so small. So if we have a higher, like normal, 100,000 micron square per minute diffusion coefficient, it will not affect that one, and we cannot see that differences because the diffusion coefficient is so high. So therefore, for this one, we will just use 100, and there is no decay rate. The initial condition will be 38, and there will be no Dirichlet boundary condition on the boundaries, and we would like to track the internalized internalization in the agents. Yes. So this was oxygen, and in the glucose, the diffusion coefficient is 3 times higher, which is kind of like scientifically true when we look for the relation between the glucose and oxygen. And decay rate, there will be no decay rate. The initial condition will be not in here. This will be kind of, I'm just making arbitrary units in here again. This is more kind of like qualitative model. And there is no Dirichlet boundary condition. And yes, we would like to track in agents. And the last one will be lactate. Even though in the beginning there is no lactate in the model, we would like to define the chemicals that will be secreted. So therefore, we need to define the lactate. So the diffusion coefficient will be same in the with glucose. Decay rate will be 0. Initial condition will be 0. There will be no lactate, and Dirichlet is off, and this is the microenvironment tab for us. So in this cell, in this demo, there will be one type of cell, and we will seed them as a blob. So with using custom modules. So as a default, I will just leave it default because I called like this, I believe, in the custom data, and then the cycle model will be leave. There will be just one phase and one phase link, and the transition rate will be used, and it will be 0 in the beginning, or like in the beginning there. So we are set the the cell cycle rate as a 0, and there will be no death, so death rate will be 0. Again, the transition rate is 0, and this is the index for the apoptosis, I believe, and the transition rate will be 0, 0, 0, all 0. There will be no death field. They will just be staying there in the beginning. There will be no change in the volume and mechanics. Therefore, I'm just passing them. And as a motility, also they will be staying there. They will be there. So I'm not sure actually, like, should I enable? Okay, let's enable the motility, even though it's not here. Enable motility because they will move eventually. So enable motility should be on. And the persistence time is 0.1, and migration bias is 0.9. We are making in here, like, after we change the speed, the migration speed, they will behave these rules actually. Like the migration bias will be very kind of like high. And let's go to the secretion. And in secretion, these will be all zeros. Also, target could be 0 because we are not secreting oxygen. The uptake rate will be 0.045. And when we go to the glucose, again, we are not secreting, so therefore target and secretion rate will be 0. Glucose is kind of like relatively similar. And this was the glucose and lactate. So, okay, in here, so we will not set any secretion rate for the lactate. So we will change through the intracellular phenotypic part. So therefore, we will just leave it 0, but we need to change the secretion target because if we set this one 0, there will be no secretion. So we need to change the target, which is the saturation density. Will be 10. Okay. In here, the custom data, so we didn't actually create the other custom data. So therefore, we need to go to the custom data part. And in the custom data, this is where we will store the intracellular data. So therefore, I called intra in here. So I'm just overwriting the sample. Intra-oxy will be the this custom data that we are assigning to the intracellular oxygen. So those will be 0. So right now, these values are not actually will not affect anything because even though they are in the beginning, they will be set at 0. After we seed the cell, we will change these values. Intraglu will be glucose, intralactate, and intraenergy. All be zeros, and dimensions are arbitrary units. So therefore, I'm just not changing. Okay, the user parameters. The user parameters actually, those are just a value that we are parsing from the configuration file, and I'm just using them in here. Initial internal oxygen will be double, and this value is kind of I kind of like starting from the a kind of like balanced value. If I change this one higher, then it will just drop to these kind of values. If I make it more bigger, then it will change it. So maybe we can try after we got the simulation, but these are kind of like a balanced values for this given SBML. I hope I can make it this one bigger, but it will not. So this one, initial internal oxygen, initial internal glucose, initial internal galactate, and initial energy. So the glucose will be 15 and lactate is 0. There is no lactate in the beginning, and the energy is 450. Okay, when we go and save this one, let's see how it look like. Okay, we have these ones right, we have these ones right, it's all true. Oxygen is right. I'm just checking because there will be a different one, missing something. The definitions are right. The glucose is right. And motility secretion. Oh no. Okay, it's working. So like on morning, and also that was the part Paul's code didn't work. The custom data didn't propagate in here. So, but in our case, it's propagating. So be sure that the custom data for the cell definitions for the default cell is there. Okay, let's go to the part. Okay, so these attributes or these information can be written in the model builder, which is so good. Thanks, Randy. And but we don't have any right now actually intracellular attribute for the cells. So therefore, we would like to create this intracellular attribute for the cell. So okay, I know this is you cannot copy and paste this one. So what you can do again, you can just go and yeah, let's do it together. So when you go to your PhysiCell, and I didn't populate it, so they are there. So when I go to the settings, this is the where I am just copying. So we will change this one. We will edit a little bit more in future, but you can just go and go to the configuration file and copy and paste the intracellular attribute. I believe the location should be in the phenotype. Please don't paste after the cell definitions or so. So it should be in the phenotype. Those are just cosmetics, but Yeah, I saved. Okay, this was my model. So what I would suggest, change this one to, I know there is a backup there. Change this one to the 1, and save the model, my model in the PhysiCell model builder. So it's in another repository for me. I will just copy and paste it. It's in model builder, my model. I just copied, and I'm going to the PhysiCell and pasting into the configuration file and naming as PhysiCell settings as normal in here. So okay, yes, I can, yes. Okay, we are not looking for this one. So what I can do, I can post this one into the GitHub actually. I think that would be more more efficient to do it. Or so the thing is, I think when I save it, it's not saving. It didn't save. I'm okay. I just want to copy and paste that part. After the secretion, there is a block, so we can just save it. Yeah, you can just copy and paste it. All right, that should work. Okay, so we have a model builder created, and also we added the intracellular part manually. We have a configuration file, so this should work normally. So okay, this was for the GUI. Sorry. So this is the command window that I just populated, and I make reset. I just want to make, okay, libroadrunner is installed. Okay, it's compiling the code. Yeah, this is the kind of like the session that is building upon all the things that we learn. Yes, I will do. I will do. Thank you. Okay, so OD energy is created. So I'm just simulating, and I hope it will work. So maybe I can just kill in here. So these ones, these displays are showing that it is just reading the SPML and looks for the indices, and those are the values that are read from the SPML. So it created. Okay, it reached the 30 minutes. It's actually proliferated. They proliferated, and they are again reading the SPML and starting the oh no, oh yeah, we should. So please be sure that in the configuration folder, this toy metabolic model is there. If you populate like I do, it should be there, but I just want to make sure you're there. So because it's making so many calculations and so many updates, it takes some times. And also, please be sure that you have a Copasi is installed, because this is the way we will change the SPML. And then okay, I believe Farnoosh, you are in Linux, and Randy, do you know, or have you seen this error before?
Yeah, this sounds like he needs to set his load library path.
Okay.
An environment variable. So if you look at the quick start, we describe how to set the DY. Yeah, I think he knows. He's a Linux person.
Okay.
They know everything.
Okay. Maybe while we are waiting, I will just open another. I shouldn't do it, but why not? Let's go to the PhysiCell folder in a plain Anaconda. Sorry, and I will use the beta version of the plot cells to visualize the first part of the simulation. So it looks like this: Python and beta plot cells.py. Okay, so it generates the yellow ones. The yellow means that they are in cycling part. So in the coloring function, maybe we can just look that one too. In the coloring function, if the intracellular energy custom data is greater than 445, which is cycling part, and then they are yellow. If they are less than 445, they are red. And if they are dead, as you can see, they are dead, they are black. So let's play a little bit. They are okay. So what we are seeing is right. Okay. So yeah, the model builder actually helps us to build all these stuff, and then we just need to add the intracellular block that I will explain in a minute. So okay, the model builder is working, and okay, and in here, okay, so let's close the plot cells, and let's use plot data. So in this one, actually, what you are seeing, kind of like a distorted one, it is generating both a visualization for the microenvironment and for cells too. So as you can see, like those are depleting oxygen, and oxygen is coming less and less, and they don't divide, and so you can go and look for the lactate. When we play, so they are secreting lactate, even though, as you remember, we set the lactate secretion 0. They are actually secreting some lactate. Okay, that's so good. All right, so does anybody have a question or any frustrations that didn't work? You can just unmute yourself and just ask a question, by the way. Okay, so this was the kind of like basic, but we did actually all intracellular part. So let's go to the second second part of the session, which will be more interactive. Okay, so the agenda will be SPML creation, and we already did the population of this sample project, and we will remove the some part of the custom module. And sure, yes, I can do it in a minute. Yes, and we will code together. Let me put the slides on. To the GitHub folder. I'll just stop my sharing and then do it very, very quickly. Okay, it's done. Okay, that's so good. All right, let me share my screen. So I just want to show where it is. This is our GitHub folder, and it's in PDFs, and the section 11 was the previous one, and that also has the basic domain, and this one is more kind of like a Copasi related one. So, all right, let's go to the session 12. All right. So okay. So actually, I gave you the pre-created SPML, and therefore it's worked. So, but how we can create the SPML, or how we can edit the SPML itself. So, and while we are creating, actually, you will see the intracellular part of the model. So that model actually, that we created more kind of like agent-based modeling part. So let me open this one. Okay, should I? Okay, here. Okay. So these ones are also in the in the slides, but to let me see if I make this one. Okay, it is working. Maybe I can just zoom in, zoom out. Okay. So for those who are not familiar with Copasi, actually this is the SPML editor, and also you can simulate the SPML in it. And in each SPML, they should have compartments, species, reactions. They don't need to have global quantities or events, but those three were important. But we will have the global quantities and events in it. So okay, so actually what we are, so it should be 0, 0, all ones. And I started with starting the intracellular compartment. So in here, there will be just one intracellular compartment. And okay, also, yeah, and also they will be online, by the way. But I think we have, yeah, we have enough time. But so the value will be 1. Yes, they are in the GitHub. Okay, the intracellular compartment. Actually, like what I did is just I typed the name as like intracellular, and the value will be 1 to get rid of the calculation. Just it will be 1, and the species will be actually 8 of them, but 4 of them are related with the more intracellular part, and 4 of them are related with the more agent-based models part. So let's start with glucose. Um, Glucose, it will be intracellular, and the value is 100, but this will not affect. So that this is a kind of like a thing that I put because um, we will overwrite this value while we are seeding the cells. So, and then let's go and create the oxygen. So I have a distinguishing actually in here. As you remember, in the PhysiCell, we set the name in lower cases, and in here we are starting with capitalized, so it will uh, I just want to make this distinguish to make it easier. So energy will be 400, but again, those initial conditions will not matter because we will override. And lactate 0. Okay, those were the chemical reactions. So we can populate, we will write these ones after we set the reactions. So let's go to the reaction part. So when you can also toggle in here like this. When you go to the reactions, there will be 3 reaction, and aerobic and anaerobic. So you can write the reactions in here actually. um I'm just writing straightforward like oxygen, and this arrow means that this reaction is irreversible. 38 energy, and let's make it our anaerobic glucose 2 energy plus lactate. So while you are creating, if you make a typo, actually, it will automatically create a species. So be careful. So if you make a typo in here, then you need to set the things out and then remove the typo name species in here. And we will have an energy usage reaction. This is the name of the reaction, and reaction will be energy. Species will be just consumed, and those will be all mass action. So in the normal case, always there will be more fancy chemical kinetics, but in this example, it's just mass action. Okay, so let's go to the global quantities, or maybe we can just look in here. So to make it easier, maybe we can look for the anaerobic one. So the glucose will be changed into the 2 energy and lactate, and this is the formulation is actually the K constant, the chemical coefficient for that mass action kinetic, and then just the concentration of the glucose. So so if we actually create an let's create aerobic constant first and then anaerobic. So you can just go to the reactions, and then if you go to the mapping, you can just select the global quantities. Global quantities is more for the parameters and constants, or also the things that is calculated more like normally. But the species are kind of like in ODE. Does it matter that you used all lowercase in PhysiCell but are capitalizing in here? That's a great question. That's actually the reason why I am using in that way. We will use mapping in the settings, and while we are using the substrates, the firstly we need to give the substrates, and I just need to have a distinguished way to between them, and like the all I capitalize, and so if you can actually has all lowercase, but you need to write in here as a like lowercase. So this name should match the SBML name that you will create, that you are creating. Okay, I'm just creating the, let me go to the PowerPoint. I'm just creating the other usage, other kinetic parameters. So again, those are not kind of like scientific parameters, but I came up with maybe like I made maybe like 10 hours or so trying so many different parameters to have to see the behavior that we would like to have. So um, therefore, like these the Arabic one has a higher constant, but the K usage is like this. Okay, so those parts were all related with chemical reactions. And the next thing that we will add, the 4 species and events and the global quantities will be more related for the update part, update phenotype part. So let's go back to the species. Okay, so in the PhysiCell, so when we use actually LibRoadrunner, can you input reverse reactions? Sure, I can try after we got the result. I just want to take a note. Yes. um, yes. Okay, so after this point, actually, so the thing is, PhysiCell knows only the species. um, PhysiCell cannot actually look for the global quantities. And also, there are types of species. When you go in here, it means reactions and OD and assignment. PhysiCell cannot see actually not PhysiCell, LibRoadrunner. LibRoadrunner cannot see the species that are not reactions. So please be sure that this is reactions. I just want to say that because if you, for instance, why uh, we are not defining the apoptosis rate as a global quantity is because, again, like LibRoadrunner doesn't give those information for us. And okay, those are all right. So let's create the other one, apoptosis rate will be 0. This one kind of like important. I should maybe, oh, typo in here, apoptosis rate. All right, migration speed. Okay, this is very badly written, sorry for that. And the transition rate. Those are all zeros. Okay, we created the species, and let's go to the global quantities. So those will not be used in any chemical reactions. Those will be just used as a user, as an interface, not user, as an interface between ABM and kinetic modeling. So let's go to the global quantities because we will define the thresholds, and those thresholds are these thresholds, the energy thresholds. Okay, the global quantities are energy mu thresh. So we will use these global quantities in the events. So that's why actually we are defining in here. Energy death thresh and energy prolif thresh. So the name should match in here. I think. Yeah, no, the name doesn't matter. Sorry, the name doesn't matter. The name should be important for the species, not for the global quantities. Okay, so we have the some values when they are fixed, and let's put some events. So the event part, actually we need to set 6 of them because the first one will be cycle, divide, or don't divide. So let's create an event. So you need to click, double click, and the trigger expression will be look like this. Let's name the event. Let's make it divide first. And to select the species, there is a button in here, Copacity logo in here. Then you need to go to the, so this is actually like taking the variable name in proper way. So you can write the name in their syntax, but this has a kind of like user interface, so why we are not using. Okay, the species and the transient concentrations for the energy. So this is the syntax for the transient concentration of the energy. The concentration is just value. I know there is no concentration of the energy, but it's called like this. If the energy level is greater than, then we will go to the global quantities. Let's make it transient values or initial values. It will be fine because we are not changing those values. And then make it proliferation threshold. Okay, so we actually set the rule, and if the energy is greater than the proliferation threshold, then the target will be species, transition constraint, and transition rate. So in this case, the transition rate is 1 hour, which is, or it's not a 1 hour, it's 10 hour, I believe. Okay, we set the target and we set the expression. So normally, again, if you would like to make a more fancier thing, you could have some relation for the species with a different stuff. For instance, like let's say uh, the oxygen level will be kind of like multiply, or maybe multiply by some values, and then this value will be migration speed or something. You can just look write a fancier mathematical equations like this, or you can just use a if thing in here, divide or not divide. Yeah, while I'm just creating those, if you have questions, please ask. So don't divide will be energy less than proliferation threshold, and target will be, again, transition rate, and in this time it's 0. So why we are making this, if I don't specify this don't divide event, after they will firstly reach their energy threshold, they will go, and then always will be staying in this one. So therefore I have one or other cases in here. Okay, so I think one thing, maybe we can just simulate this one. Why not? All right, let's go and export this one to the PhysiCell that you have. I have directly it's PhysiCell, and it should be located in the configuration file. And let's call this one demo SBML. Why not? It should, yeah, it will. So after some version of the model should has their creator. So I'm just adding myself, and then I should be able to save in the latest version of the SBML. Okay, I have that one, but it was a lower level. Didn't I create? Maybe don't. Oh. Okay, then it's working. Okay, Reshma has a question. Is it possible to add different SBML files for different cell types? Yes. Each cell can have their special types of SBML. So therefore, if you are creating another type of cell, you will have a different cell definitions, let's say fibroblast, and it will have nearly all of them, these ones, if you are not using the parenting. And then you just need to change the SBML name in here. And then therefore it will directly use that SBML instead of that one. So while we are here, so let's change the name of the SBML that we created. I just want to be sure demo SBML is there. Demo SBML is here and has all the stuff in it. All right, let's take this one and go to the here. And I changed the demo SBML. So we will see so many bearings. So let's see, this is for GUI, so I can just close it. Sorry, Randy. Okay, this one is the one. And okay, let's make data cleanup first. Okay, and it's ready to go, just OD energy. So what we will see in here, maybe it will take more thing for us, but they should all divide, and they are not dividing. That's interesting. Okay, they are not dividing. Did I put a small value there? So this is how we change. So we are just going to the related parameter and change. And right now it's I think right now it's 60 minutes. And then export SBML as again demo SBML, and you can just overwrite it. And let's go here and okay, it's seeded all cells, and let's wait for kind of like 60 minutes, and then we should see the proliferation or not. Huh, interesting. Okay, why is that? And also you didn't do cleanup. I did. Oh yeah, yeah, so because I am just overwriting the value, so I just want to, yeah, you're right, but I don't need to actually, because I'm just passing that time. So in the previous one, that was all simulation. So if I kill the simulation before it simulated all the time, so it would make a problem. But in here, it's just first ones. That's a great question. That's a great one. So let's make this one a bigger one. Export SBML, demo SBML, and the thing worries me actually. We didn't see any errors because, oh no, we have all of them. We have all of them. Okay, that I understood. So because we set the apoptosis rate to 0, or no, that doesn't make sense. Okay, no, sorry. So let me make data cleanup. And OD energy. Interesting. And let's have plot data. Okay, the thing is, they start dying immediately. Okay, so I have, okay, so the thing is, when you populate the configuration file, there are two MATLAB files that I wrote. So you need to, I'm sorry, maybe we should, Randy, this is my bad. These should be in the main folder. You can just copy and paste to the main folder. And I have a I have a MATLAB file. You can just look for the domain, and it will produce the temporal average values for the energy. So let's look what's been there. Okay, we should have very small thing. Okay, energy is starting from 33. Why is that? Okay, let me go here. Did I remove something in here? Okay, it should be 450 and initial energy is here, and we set that one. Okay, what I will do, they are starting dying actually. Why they are dying? Huh. Let me here. The apoptosis rate is here. Transition rate 0. It's fine. So maybe I made a mistake while we are creating the oh, that's why I didn't assign the global quantities for the reaction. Oh my God, I'm so sorry. So okay, after we created global quantities for the reactions, I didn't assign the related constant. So this will be KAR, and this will be K usage. And let's commit it and then try again. Okay, now they are dividing. That makes sense. Okay, so sorry, but it's good to be figured out. Okay, so let's make it this value like a normal value. I believe this was the value. Let me check it again. 3 zeros. Yes. Okay, this is the one. Okay, right now they shouldn't die or move, and we are not saving any division again. Is it too small again? Okay, they divide. That's fine. Okay, that's good. So I just want to wait a couple of iterations to visualize. Okay, now they are dividing, as you can see. So this is a stabilization, and some of them are dividing. Okay, that is kind of working. Okay, so let's go back to the SPML part. The working part is here. The CTR cycle transition rate between the zeroth or the one the first phase and the second phase, and again first phase, because it's just one phase and it's just dividing, and the transition rate is the name of the SPML species in SPML, and this is the thing that we are changing, and I think we are just lacking for events, and let's add them too, and then we are creating actually SPML and um, the configuration file from beginning, and then we will go and look for the code. Okay, die, don't die. Or no, there is no don't die. There is die, just because if the energy is less than that threshold, and this should be transient concentration. If this is less than that threshold, which is 430, then the target will be apoptosis rate, and this apoptosis rate was, okay, this is the part actually I just want to explain. So in here I set it and like direct dying. So this is how we do in PhysiCell. It's 9E99, just instant entering the dying phase. Again, let's try this dying SPML dying rule, and I can kill this one. So we need to wait a little bit to consume the energy, and then we can just visualize with the PhysiCell visualization. It's working so great, Randy. I'm so happy. So after they reach the motility energy, they will be colorized. They will be colored red, but they will not move because we didn't actually add that one to our SPML. So let's play. Okay, they are dividing. Some of them are lucky ones. And they are still. Okay, Kana has a question. Can custom functions be used to change the values of these reaction rates during the simulation based on cell conditions? Yes. Yes, like definitely, because the update intracellular function is called in some intracellular DT, and this is how it looks like. I just want to just briefly show the values. So we are doing so some indexing, getting the cell volume for the concentration, and getting the um, concentrations, and setting the SBML in here, and then SBML simulation with update. And then we have the phenotypic simulations. This is the phenotype update phenotype function that we have in add-on. What you need to do, you need to just give the all cells and then their phenotypes as an input. And after we change their phenotype, so maybe you might want to change over like before here if you would like to. And then we are just saving the data to the internalized one, because we are updating the intracellular, the custom data in here, and saving the custom data. So in here, internalized chemical update to the total substrate sets. Like this is what we have. All cells. This could be P cell, by the way. This is how I wrote all cells and phenotype, because this is a for loop that is running all cells and index of I, and index of I in here. Um, phenotype intracellular. I wrap the line in here and get parameter value oxygen. So I'm just getting the oxygen values and multiplying by the cell volume to have the total substrate in here. And then I'm just updating the custom data to save the data, so to save the intracellular. So if you would like to change the um, some value after the reactions, so you can just write some calculations before the phenotypic update, like this. So all cells, set parameters, oxygen. I think let's say you would like to change the oxygen or energy itself. I don't know, energy itself. You can set the energy value of something that is coming from here, like maybe energy based on some glucose level, I don't know, like this, and then it will set the energy level based on the result that you currently have. Okay, so that was a great question, because also we touched the code a little bit while we are waiting for the longer simulation. So, all right, they are started dividing, and some of them, like in the middle, they actually okay, they started dying. So what their energy level less than motility threshold, and then they less than the death threshold of those ones, and those are just dying, and some of them are again. And this is why actually I set the diffusion coefficient small. If we have a 100,000 diffusion, so they will just have very high oxygen levels or so. So that's why I put this one. So okay, so I think if you have any questions about these ones, I will just change to the normal one instead of creating. So maybe I can just show the normal one, and so we wrote the divide, we wrote don't divide, divide and don't divide, don't move is greater than, if the energy level is greater than threshold, then it's zero, the migration speed. And if the energy level is less than more move threshold, then just change their migration speed to 10. Again, these are just values, but they can be estimated with experimentally. So this one is kind of like an interesting one. So when we go here, so when I look for the lactate, I shouldn't see any lactate secretion because we didn't set this rule. So this is how what we are seeing actually. So there is no lactate secretion because we didn't update the lactate secretion rate. And so this is how I put the event. A lactate, if lactate, intracellular lactate is greater than some value, then the expression is just value. So this could be changed by something. So this could be some calculation, and based on that calculation, that secretion rate can be changed. Also, don't forget we can set this secretion. We can set this one to the uh, to the net export rate. Also, if you have a transfer reaction that is just following the in the name of in the amount, you can just put I believe it's instead of SSR. Let's look, not this one. Here, did I miss it? Net export rate is SER, and then the name of the substrate in the PhysiCell. Okay, so therefore I am just backing to the normal, like the one that we have, the toy metabolic model. So I just want to say that, notify that this one has the wrong values. I will try to update this one, but this is in sample project. If you populate it, this wrong capacity folder will be populated. So don't pay this attention. This one, the important one, the is SBML, which is the correct one. So it shouldn't affect that one. Okay, I'm just taking the name and changing the SBML to the normal one, and going back to the custom values. Okay, so I'm just taking all back, and this is where we are. All right. If you have any questions, again, you can ask me, and the Copasi part is done. So therefore, to save or to export the SBML, you need to use export SBML, and let's remove important part of the codes. So in the code, we will not, for right now, we will not change main. Main is just there. And also, we will not change most of the custom modules because those are not related with this topic. So the part is, maybe do I, so the thing is, maybe I can just explain instead of writing one by one. I can, because we have 20 minutes and I would like to show a couple of things too. And I know this was a long session. it's so much things to explain. Okay, so let's start with setup tissue. In the setup tissue, we are starting with the substrate indexing. So these are just manually doing. We are just learning the oxygen substrate index based on the name in the PhysiCell, because this is all PhysiCell, and we learn them, and also we learn the so there is a function that I'm calling create cell circle positions. This is actually kind of like at the bottom. You will see this one. This is creating a position vector for a given cell radius and initial tumor radius, and also like it produced that number of positions, and then after we have the positions, so if I increase this tumor radius, let's say make it 20, then the number of cells will be higher, very higher, and the for loop is just turning on this position vector and creates the cell taking the cell default from here in the same name, and then I'm just looking for the intracellular concentration custom data. I'm just actually again looking for the uh, indexing here, and then I'm just writing the custom data. Um, I'm just writing the initial internal values that are placed in the user parameters. So therefore, I'm just overwriting the custom data that we created, and those are the values. So after that one, I got the cell volume, like in this syntax, and then um, just um, multiplying by volume and overwriting what we have in the total intracellular total amounts. This is where we are changing in the first iteration. So then I'm just starting the intracellular. This is just reading the SPML and adding the libRoadrunner structure to the each cell. And then I'm just setting the parameter to the energy. Why I didn't do this one before uh, I do it, because I am not actually in the update intracellular, I am not actually changing the energy level. So in the first iteration, I need to change the energy level in the beginning, in the initial spec. That's why actually I just set the parameter value in the name of energy. This E is again in the SPML, and the given energy, initial energy. Okay, this was the beginning one, and still we are in here. So we did some setup tissue. This was the part we are, and we did some saving part, like creating some folders, files, and not folders. And then this part is just again like those are doubles. And then this is the main loop, and we are going and going, and this is the first thing that we are facing, the update intracellular, if the conditions are met, if the intracellular is the one. So in the intracellular, I just want to just again here we are doing this in the updating part. So we are learning and the internal metabolite concentration, and then updating the SPML and simulating it, and then updating back to the internal metabolites. So therefore, we need a bio FVM indices for the internalized substrates, because again phenotype.molecular.internalized substrates, total substrate, are the amount that we have in each cell. So therefore we need these indices. So these are actually not important, so these are not used. They were old version. We need to remove this one. I need to take a note. But okay, so this is the for loop that is just going on all cells. And again, we learn the custom data because we will set the custom data in this SPML. So therefore, we are learning or no. Okay. I'm so sorry. This is not used until the saving part. So this is, yeah. So, okay. This one, so this one is not true. This one is like this. We are changing intracellular substrate instead of concentration. Okay, we have cell volume. We actually go through, we are learning the intracellular concentration in the cell. This is from PhysiCell. We divide it by the volume, and we are setting the parameter into the SPML. We are setting the oxygen, glucose, and lactate. Right now there is no automatic way, but in future there will be, I believe. because we can just take the names or so. So right now we are setting each species one by one, and then simulate the SBML, and then update the phenotype, and then change the chemical, internalized chemical based on the simulation result, and get parameter value oxygen, and oxygen substrate is the BioFEM in this. And for the saving purposes, we are just writing the custom data, and we are saving that one in the normal one. So I just want to, while we are here, want to show how we are saving. So let's go to, is it still going? No. So when we go to cell PhysiCell, there is cells matrix, which is very big. So, okay. So when you go to the each XML, the indices are there, but I just want to show that the last four is usually the custom data. The last ones are cell custom data, and those are the values that we set. And 450 was the last value that we set for the energy. So this is how we store the data and save the data. And then I am using just parsing the data to have some average values. So okay, so yeah, if you have any questions, please ask. But my purpose was just writing these one by one, but I think we have 10 minutes, and I just want to show something too. Let's go and here and PhysiCell settings, and we have toy metabolic model as an input. And okay, let's make data cleanup and then save and then simulate. Why? Is it this one? Okay, there is none, so it's fine. Oh, the energy. Okay, we started with initial values. So yeah, you can find this intracellular visualizer in the configuration, but you need to move it one below, one above. Okay, I just want to show how to change intracellular DT, because we talk about this one a lot actually. While we are having this one is going, I can explain this one. All right. So this is the main file, and we are manually giving the intracellular in here. So what we need to do, we need to change in here. This is 1 minute. This means that we will call update intracellular in each minute. But if we left the like this, the thing will be like this actually. Okay, here. So again, this is our T, this is our something, and again, this is accumulated or maybe added some chemical uptake in the in the cell, and it's let's say it's 1 minute, and we didn't actually have the intracellular still. So if we leave like this, the libRoadrunner as a default is just using DT as 0.01. So therefore, after 1 minute, the intracellular function will come and just will come once. And like this is too big. It should be very, very small. Just one iteration in 0.01. So therefore we need to change the solver too, and I want to show how to change it. So when you go to the LibRoadrunner Intracellular, this is where is located in add-ons, LibRoadrunner, source, and the CPP is the one. And when you go to the update function, what you will see, it's again, end time is manually written as 1. So this will be changed in future very, very soon. We will just give this one as a like an input as a DT, but right now it's manually written. I just want to show this one. So therefore we need to change the solver and time too. So the solver is just, by the way, just making one iteration. Two means the first start, and end is the second one. So it's just actually iterating once in that DT, in that given DT. Is it still so big? No, not this one. So this is the one. Yeah, it's taking some time. And it took more than 4 minutes, so we can just visualize it normally if it is working. So this is the lactate, and they are excreting the lactate, and it took more than 4 minutes. And I just want to be sure that the everything is working fine. So those are the energy less than values, the threshold. They are starting to move, and some of them are dying in, this is 13 hour, and some of them are just going there. And if they are lucky, by the way, they can just have higher energy when they have the higher energy there, like when they have a higher oxygen and glucose. Okay, so this is working. So all right, so one thing I want to, this is the last thing I want to show. So we, in the main file, we change the intracellular to 1, and in the solver it's 1. So let's simulate, and we need to compile because we changed the code, the C++ code. And let's make it ODE. See, it's so fast. So if we iterate in 1 minute, it's so fast. So the previous one took like more than 4 minutes. This will take maybe less than a minute actually. And also I will show the results. I know we didn't make data cleanup, but if we wait and until end of the simulation, we can just visualize this is a bad behavior, I know, but it will not make a mistake if we wait until the end of the simulation. Okay, yeah, it took 50 seconds. So, and let's see what we have as a result. Again, this is lactate. Maybe we can change it to the oxygen or so, but it's fine. They are excreting lactate. And some of them are starting to move. Yeah, it is the same behavior, but again, there are some differences. So this is the user part actually. So what we can do is again we can temporally simulate, temporally compare the simulations um, for the average oxygen and glucose or energy. Yeah, the first one is, yeah, this is the oxygen and this is the energy. So if we are above 445, they are dividing and dividing and still dividing until the 450, and then they cannot divide, and then they started to move, and then they started to dying, and again like their energy is coming, and then um this is the behavior I need to look a little bit closer, but because they die and some of the lucky ones are in the middle, they increasing their energy because of the glucose, I believe. And the mean oxygen is increasing and decreasing. Um, yeah, I think that was the part that I would like to show. Um, yeah. Yeah. Okay. I'm in time. That's so good. If you have any questions, you can ask. We have 3 minutes, and also you can ask me through Slack or email. Shot me an email. Um, that was all. Thank you very much. Thank you. Thank you very much. And I believe the next session will start in 15:45. We have a big break for the lunch for the western part, and then let's meet on the bigger collaboration room. Thank you very much, guys.